All right, 8-2, we're adding on. So we were just multiplying, dividing rational expressions, but now we're simplifying complex fractions. A complex fraction is a fraction in which the numerator and the denominator both contain fractions. So basically, it's the idea that you might have a fraction divided by a fraction, or fractions in fractions. That is your complex fraction. So how do we deal with this? First, we're going to factor everything that can be factored. That includes taking out GCFs, difference of squares, reverse FOIL, sometimes some trial and error. We just talked about watching negative signs. If your leading coefficient is negative, take out the -1. We're going to rewrite the problem as horizontal division. You could skip this step. We'll talk about it both ways. But the idea is we're going to then change it to multiply the problem. Keep, change, flip. So the idea, what we talked about yesterday, is we never divide. We multiply by the reciprocal. So consider the following problems. I have 5 divided by 20. I could always write that as 5 over 20. And we would reduce that simply to 1/4. And I can write 10 divided by 30 like a fraction, and that is 1/3. And 2 divided by 4 is 1/4. Now, any fraction that I have, I can always write as division horizontally. So that's the idea of the horizontal division. All right, I got caught. I messed up. This should be 1/2, which we know. All right, all of these can be simplified into a fraction, which we did. But what about 30 divided by 0? That is the same as saying 30 over 0. What's wrong with these quotients? Quotients, the answer to division problems. I can't divide by 0, so we call this? No. Undefined. Just like the slope of a vertical line is undefined because you have a rise of 1 and a run of 0, and you can't divide by 0. So I can have 0 over 2. That's 0. But I can't have 2 over 0. That is undefined. Okay? So can't divide by 0. This is called a domain restriction. All right, domain is what X can be, what your input is. A restriction is X can't be this. So domain restriction, I use the abbreviation of DR just because I don't want to write out domain restriction. The domain restriction is the idea of what X cannot be, or what the input cannot be. And when I say input, we're talking about the X value, but you could have different variables. All right, the domain restriction is always going to come from the denominator. So domain is what it can be. The domain restriction is what it can't be. And it's the idea that you cannot divide by 0. That's where our domain restriction is coming from, the fact that we cannot divide by 0. So if you look at this example here, this looks like what we did yesterday. We have x plus 3 over 2x. There's nothing to factor, nothing to cancel. But my denominator, 2x, is not allowed to equal 0. So there's my cannot equal. And if I divide by 2, that means x cannot equal 0. So that is my domain restriction. Here is my answer with a domain restriction. X cannot be 0. And yes, I will be picky about that. You can't just write 0. You can't write dr 0. You're going to say dr for domain restriction and state that this variable can never equal 0. Now, is it okay if x is 3? Yeah, 3 plus 3 is 6. Is it okay? And that would be 6. Is it okay if x is -3? -3 plus 3 is 0. Divided by 6 is 0. That's fine. But I can't divide by 0. Your domain restrictions are always going to come from the original denominator before you cancel something. So look at this first problem here. First, calculate any domain restrictions, then simplify it. Domain restrictions are coming from any denominator. Now, here's what I need you to think about. You have a denominator here. That's obvious because you're dividing by 8x to the third, and this is a denominator. Agreed? But there's one more piece here that we have to consider, the 3y. So you were dividing by xy, but you're also dividing by 3y and dividing by this. Because if you think about it, if 3y is 0, then I'd be dividing everything by 0. And I don't think that's real clear. Still not? Okay. Now, I do have two variables, and sometimes that can be a little bit complex. The domain restrictions are going to say this piece right here, xy, Oh, I went too far. Xy cannot equal 0. Okay, well, that just means simply that x cannot be 0 and y cannot be 0. All right, look at this 3y. This piece, because we're dividing by 3y overall, cannot be 0. Well, that just means y can't be 0. So that's a repeat. And then I have my denominator of 8x to the third can't be 0. Well, if you divide by 8 and take the cube root, x can't be 0. So what's my overall domain restriction for this problem? The x can't be 0 and y can't be 0. Now, I know we're talking about domain, but in this problem, x and y are both input, okay? So it's the input that can't be 0. Now, come back over here. If you want to show this, you can. 6 over xy divided by, so instead of showing it as a big fraction, 3y, 8x to the third, they said show it horizontally. No matter what I show, I'm going to keep, change, and flip. Instead of dividing by a fraction, I'm multiply by the reciprocal. So no cross canceling. You can't reduce or do anything with division. You've got to do your keep, change, and flip. Now you can cross cancel. So just like yesterday. And then what does cross cancel? Let's look at the numbers. 3 goes into here once and into here twice. I've got an x down here and I can knock it down. So what's left in the top is, if you want, 2 times 8 times x squared. What's left in the bottom is y times 1y. So final answer, 16x squared all over y squared. And our final domain restriction, x can't be 0, y can't be 0. So I should have the work to show what I did, and then I should have my final answer with the domain restriction. You could have skipped this step and gone straight to keep, change the sign, and then flip the fraction. All right? All right, flip it over. First things first, it's telling me to find the domain restrictions. Here's what I'm going to do, guys. I'm going to go ahead and clean this up. I'm going to do it all at once, but if you need to do a little bit more breakdown, you can. I'm going to leave this 18p over, and then this is going to factor to what? Can I take out a 2? And I'm left with 4p minus 1. And then I'm going to go ahead and flip. Now, if that's going to throw you off, don't do it. My denominator is now 4p squared, and my numerator doesn't factor, it's 4p minus 1. So I did skip some steps, but you could do that. So another time I did it, I have my numerator divided by my denominator. I did my keep, change, flip, and I factored at the same time. All right, go ahead and cancel anything you can. All right, so what are we canceling? Definitely the 4p minus 1. Agreed? What else can you cancel or reduce? Well, it depends on how you see it. You could reduce the 18 and the 2 or the 18 and the 4. I'm going to go ahead with the 2 goes in there once. It goes into here 9 times. So I'm looking at one more thing, and that's that one p here cancels with one of the p's here. So what I have is just a 9 on top, and the bottom is just a 4p. Okay, let's talk about our domain restrictions. And now these have to do with p. So notice I'm saying here's the domain restriction, my variable's p, and this is what it can't be. All right, your domain restrictions are coming from everything you divided by. So you were dividing by this, you were dividing by 4p squared and 4p minus 1. So if you come off to the side here, we had the 8p minus 2, which we factored to be a 2 and then a 4p minus 1. Set that to not equal 0. Well, what's my domain restriction? 2 will always be a 2, but we don't want p to be 1/4. Remember how you add 1 and divide by 4? Okay. Then we had the next piece, 4p squared. Okay. 4p squared cannot equal 0, and you told me p cannot be 0. You can divide by 4 and then take the square root. It's all going to end up being 0. And then the last piece was 4p minus 1. It's a repeat. Yep. So we would get, again, P cannot be 1/4. So I don't need to list the same number twice. So my final domain restriction is going to be 0 and 1/4. So the order does not matter, but it's really important that you're stating that P cannot equal these things. But you're solving it the same way you solve a quadratic, finding the roots or the zeros, what would make it 0. Okay, so look at number 3. These aren't real complex fractions so far. Again, if you want to write it horizontally, go ahead. I'm going to jump right into the keep, change, flip. So I have k minus 1 over k times k on the top. And wait, this factors, doesn't it? K plus 1 and k minus 1. Okay, what can cancel here? Well, the k's can cancel, right, individually, and the k minus 1. So write me your final answer. Final answer. If you write k plus 1 as your answer, you just got it wrong. Where's that k plus 1 left? So what's on the top? A 1 has to be on top. Okay, I need what k can't equal. These domain restrictions are coming from 1, 2, everything we divided by. So if you think about this, when you multiplied by the reciprocal, this was your original denominator from the numerator. And then this was your original denominator from the denominator. And this is what we're dividing by. All 3 pieces are domain restrictions. Can't really read that well. So this k, if we're going over here, that original k cannot be 0. The k squared minus 1 cannot be 0. And again, k can't be 0. So you can write this all out, but I like to use what I have. Everything that I have is factored already. My domain restriction states that k cannot be 0. There's a 0 again. K cannot be positive or negative 1. So you don't have to write your domain restriction off to the side separately. You can just sort of look at each piece as long as you're finding the right pieces. Okay, look at number 4. I'm going to look at this top and think it's a little out of order. So I'm going to take a second and rewrite it as negative 15 r plus 15 over 15 r squared divided by 12r minus 12 over 1. I want to show that this is over 1. Now, you don't have to show all this, but I just wanted to show you what I'm doing. I'm going to take out that negative 15. And then what's left is r minus 1, and that's really important. All over 15 r squared. Times, don't forget the reciprocal, so 1, and what's the GCF here? 12, and I'm left with r minus 1. If I didn't take out a negative sign, I might not have caught this because this would have been the wrong signs in the wrong order. So I like rearranging it standard form. I like to factor out the leading negative coefficient. Okay, what cancels here? Well, the 15s cancel, right? But I am left with the negative 1. The r minus 1s cancel. You could have canceled the 15 and 12 to reduce, and you'd have to keep reducing. What do I end up with? Negative 1 over 12r squared. Where is my domain restriction coming from?
It's coming from the 15r squared.
All right, so it's the numerator we're not dividing by, but I am dividing by this, and then that's always going to be a 1. So my domain restriction is coming from every piece that was dividing. And if you think about it, that'd be here, my original denominator. This was the numerator, and that was the denominator. So what would make this 0 if r was 0? 12 will always be 12, but r can't be 1. So your final answer should go along with a domain restriction. Okay, I would like you to take a look at the next one and get it started. So think about factoring, think about keep, change, flip, or multiplying by the reciprocal. So if it's too much, do it in pieces. You could do your keep, change, flip. You could factor all the pieces and then do it. whatever works for you. Now, I do see I have a GCF here, so I'm going to do this up to the top. M squared minus M minus 20. And then I'm going to come down here and go with my factoring. So 2, and then I'm hoping you have M minus 5 and M plus 4.
Yeah.
All right, so that's good. Let me get rid of that pen. And then this denominator has a GCF of 3, and then M plus 4, times, now I need to remember to flip these. This has a GCF, I'm going to put it down here, of M squared, and that leaves me M minus 5. Now, this goes no further, okay? But sometimes we're left with a difference of squares, so look for that. This is going to go up top. It has a GCF of 9M, and I'm left with M plus 4. Again, it goes no further, but we should double check. Okay, what cancels here? Any top to bottom cancels. So I saw this one. Maybe you canceled these two, but it's a 1-to-1 ratio. You can't cancel 3 of them. And the M minus 5 cancels. Anything else? There's more. So we canceled out common. Yeah, we canceled out common binomials, but don't forget the monomials. So 3 goes into 3 once. It goes into here 3 times. And what about the M's? Knockout 1, knockout 1. So when you have those monomials, we can reduce them. So what's left is a 2. So if it helps you, write it out. What's left? 2 times 3 times M plus 4. What's left on the bottom is just an M. Your final answer should look like 6 times M plus 4 all over M. Or, and I'm fine with that, or the other option is 6M plus 24 all over M. You cannot cancel these M's because you can't take it out of all 3. And let's talk about a domain restriction. So you could take all of your work off to the side and show each piece, but I'm going to show it here. We were dividing by 3M plus 12, so that's that part. We were dividing by this M to the third minus 5M squared, which came to the bottom, and we were dividing by this piece, which is up here. All of those pieces give me domain restrictions. So let's just go right across. 3 will always be 3, so that's fine, but what would make this 0 if M was? -4, so it's just like solving a quadratic. 9 times M, 9's good, but M can't be 0. M can't be -4, we have it. M can't be 0, I have it. M can't be 5. So I don't have to worry about this. I wasn't dividing by that numerator, but everything that follows the division symbol is a domain restriction. Okay, any questions on that?